Let's talk about the elephant in the room. Why is it that such a massive percentage of multi-agent systems completely crash and burn within their first 6 months in production? Seriously, 40%. Look, if you're feeling total framework fatigue right now, or you're wrestling with the chaotic reality of pushing AI agents into production, this number should instantly validate your pain. It's not that the tech doesn't work. It's usually because teams either pick the completely wrong orchestration pattern right out of the gate, or they just don't anticipate how their chosen setup is going to snap under the weight of real-world scale. And man, when they break hard. We're talking about situations where picking the wrong pattern turns a 50-cent testing run into a silent, absolutely massive $50,000 monthly bill. How on earth does that happen? Mostly through sneaky traps like context window overflow, where an orchestrator just keeps hoarding context from every single worker until the token costs literally explode.
So in this explainer, we are cutting right through the AI hype. We're going to uncover the concrete orchestration workflows and patterns that actually survive in harsh production environments.
Here's our game plan. We'll look at why these agents fail, contrast workflows with autonomous agents, and break down 6 proven orchestration patterns. After that, we'll navigate some common failure modes, touch on advanced prompt graph engineering, and finish up by figuring out how to choose the right path for your next build.
All right, let's jump straight into part 1, why AI agents fail.
You know when you build independent agent loops separately without putting them under a unified graph? They unknowingly fight each other. One loop might be hyper-optimizing for blazing fast response speeds, while the other is stubbornly optimizing for exhaustive, deep-dive thoroughness. On their individual dashboards, they look perfectly healthy. But put them together and it's literally the software equivalent of a heater and an air conditioner fighting over the exact same room. Total chaos.
Which brings us to part 2, workflows versus autonomous agents.
We have a really clear trade-off to navigate here. Workflows follow predefined paths, they are highly predictable, heavily constrained, and thankfully much lower cost. Agents, on the other hand, rely on dynamic routing and model-driven decisions. That means higher latency and, higher costs. So the golden rule of production is actually incredibly simple. If you can hard-code the path, you absolutely should. You really want to reserve true autonomous agents only for those moments when the exact steps just cannot be known ahead of time.
Moving on to part 3, 6 proven orchestration patterns. First up in our toolkit is the orchestrator worker pattern. The vibe here is that one main manager agent takes the task, breaks it down, hands out the pieces to specialist workers, and then neatly assembles the final result. This is an absolute rockstar pattern for cross-functional workflows where you have clear task decomposition. Think routing customer service tickets. It gives you a single, reliable point of accountability.
Next up, we have the sequential pipeline. Now, what's really interesting about this one is this strict determinism. Agents execute in a rigidly predefined linear chain, simply passing their output forward to the next agent in line. It's a game changer for stuff like document processing or contract generation, where every single stage, like drafting, reviewing, and polishing, builds directly and heavily on the last.
Then there's the fan-out, fan-in pattern, also known as concurrent orchestration. This is where multiple agents fire off simultaneously to tackle independent subtasks. Doing this can actually cut your wall clock processing time by like 75%. Picture having to analyze a bunch of financial metrics at once. You've got agents looking at fundamentals, sentiment, and technicals, all running in parallel before feeding everything back to the center.
Pattern number 4 is the multi-agent debate. Just like it sounds, agents literally share a conversation. They challenge, critique, and refine each other's positions across multiple rounds. You want to use this for quality assurance or maker-checker loops. Basically, anytime absolute accuracy is way more critical than speed.
Coming in at number 5 is dynamic handoff. Now, unlike the top-down orchestrator we talked about earlier, this is a highly decentralized approach. The agents assess the task themselves and dynamically route control to the right specialist right at runtime. This really shines when you don't know the expertise requirements up front. Say you've got a standard customer support chat, and suddenly, bam, a simple billing question reveals itself to be a deeply complex technical issue. The agents just hand off the baton smoothly. And finally, the sixth pattern, adaptive planning, sometimes called magentic orchestration. In this highly fluid setup, a manager agent dynamically builds out a task plan, refines it on the fly, and executes it while continuously consulting specialists. Listen, you want to reserve this exclusively for highly open-ended problems with zero predetermined solution paths. A great example? Complex IT incident response, where the exact steps to fix the system only emerge as you're actively diagnosing the fire.
So the crucial takeaway here is that picking the right tool for the job is literally everything. Got clear subtasks? Grab an orchestrator. Need fixed linear steps? Go sequential. Independent parallel work? Fan out is your friend. But you really have to map these to your constraints. For instance, definitely avoid adaptive planning if your tasks are highly time-sensitive. It's all about making the smart trade-off.
Okay, let's get into part 4, navigating common failure modes.
Even with the right pattern, things go wrong. Let's punch through a few specific traps. First, you've got infinite handoff loops, where agents basically play hot potato, passing the buck forever without actually taking ownership. Then there's context window overflow, which will absolutely torture your API budget. You've also got API rate limit exhaustion from running too many concurrent agents. But the absolute sneakiest one? Sycophancy cascading. In a debate pattern, agents might just agree with the majority to be polite. Think about that. You could pay for 15 expensive model calls just to have them all enthusiastically reinforce a totally incorrect answer. Yikes.
Let's move on to part 5, advanced prompt graph engineering.
So how do we fix all those failures? Well, to truly control agents, developers are treating prompts as executable mathematical structures. You need 4 distinct conditions: explicit structure, separation, executable semantics, and artifacts. Basically, a prompt graph cleanly separates the actual orchestration from the core computation. It turns your workflow into a tangible, verifiable artifact that you can actually inspect, version control, and evaluate when things inevitably break.
And because of this rigorous structure, we can do some incredible automated optimization. Instead of a human developer pulling their hair out trying to manually tweak the workflow, you introduce a designer LLM to propose structural changes to the graph itself. Then, a critic LLM evaluates those changes based on cost and accuracy. They are literally turning workflow creation into an automated search problem. The AI is automatically optimizing how the AI agents connect and communicate. Mind-blowing, right?
And that brings us to our final section, choosing the right path.
Before you write a single line of code, please remember this rule of parsimony. Step 1. Can you solve this problem with a direct model call and just a really well-crafted prompt? If yes, great, stop there. Step 2. If prompting isn't enough, try a single agent equipped with a few tools. Escalate to Step 3. Full multi-agent orchestration only when the problem explicitly demands deep specialization or strict security boundaries. Keep it simple and escalate complexity only when you absolutely have to.
I want to leave you with a pretty provocative statistic from Princeton NLP. A single agent matched or outperformed multi-agent systems 64% of the time. Look, simplicity wins more often than not. So before you dive headfirst into building your next massive, complex system, take a step back and ask yourself, is your current multi-agent architecture genuinely solving a complex problem, or is it just elegantly over-engineered?